Our next speaker comes to us long range. See her now from Leeds University in the UK, and that's Catherine Walsh. And she's going to tell us about the chemistry which we've so far neglected much of, that is things having to do with protoplanetary disks and planets.
Hello, everyone. Thank you, Eric. Can everyone hear me okay?
Yes.
It's good. So I'm very delighted to be able to join you from across the Atlantic Ocean. I'm calling from Leeds today. So I'm going to jump right in, more or less after where Paula finished, and that's to talk to you about what we've been doing recently in the past few years to better understand the organic chemistry, particularly of these larger, more complex species in protoplanetary disks around young stars. So I'm going to give you very much the observational background, so what we have seen so far and what we've learned about disks from those observations, and also tell you a little bit about the modelling that we've been doing to try to better understand their chemistry in these environments. So we have seen several iterations of this plot today. So I think this is number 4. So we know that young stars like the Sun and lower mass and higher mass all form within dense molecular clouds in the interstellar medium. And you've heard from Paula, you've heard from Eric, and also Mike, that these are actually really chemically rich environments. We can build really large molecules in what might be considered to be a very harsh environment, very low density, very low temperature, and also irradiated by energetic particles such as cosmic rays. And once a condensation forms in this cloud, becomes gravitationally unstable, it collapses. A little bit of angular momentum that the cloud originally has leads to the formation of what we call an accretion disk around the young star. And that helps to feed material from the collapsing envelope onto the star. And also, when the envelope is finished, its accretion phase and dissipates, what's left behind is what we call the protoplanetary disk. And this is very important because this, of course, is where the planetary system around the new star will eventually form. So you've heard a lot about chemistry in various different environments already. So you've heard about chemistry in dense clouds, protostellar envelopes, protostellar cores. And what the common theme is that all of these environments show that chemistry in space finds a way to really make these quite large molecules. One of the big questions that we have in the field is, given that we know that dense clouds, protostellar envelopes are very chemically rich in these large molecules, is the chemistry that we then see in our own solar system and possibly in other exoplanetary systems, does it have its origin back in the very earliest stages of the star formation process? And there are various different theories that are discussed in the literature, such as some of the material from the dense cloud base is fully inherited by the protoplanetary disk and indeed can make its way into comets. During the disk formation stage, it's possibly modified en route through the envelope as it's exposed to energetic radiation from the young protostar forming in the center. And in the disk itself, these objects hang around for a few million years whilst the planets and comets are forming, and chemistry is ongoing in that stage as well. So there's a lot of debate over how much chemistry within the disk itself ends up then setting the composition of our planet and comet building material. So one of the, I think, holy grails of astrochemistry in the past few years has really been trying to detect these large, complex organic molecules that we routinely see in the colder, more diffuse environment within the protoplanetary disk, because this enables us to then better make the connection between the complexity we see at the earliest stages with that we see in our own solar system. So just to move on that point, we do have a lot of clues from the solar system. As Paul already mentioned, we see a lot of complexity in cometary coma, the sublimating ices of comets that occurs when they come and visit us in the inner solar system from their usually far away home in the outer solar system. This is a nice picture of comet Halley-Bopp, which has been known for some time through remote sensing using radio observations to actually be a particularly chemically rich comet. But more recently, we had this ESA mission, Rosetta, that for the first time went to visit a comet called 67P CG. And this is the first time that a suite of instruments were sent and orbited a comet for around 2 years. And comets are very important, as I've said, because they are remnants left over from the formation of planets in the solar system. And we think that they're relatively pristine objects. So they haven't been particularly chemically alterated during what we call the storage phase in the solar system. And they're important, of course, because we think they brought at least some of the water and complex organic materials to the Earth, as well as asteroids. So there was a suite of instruments on board Rosetta, particularly a mass spectrometer called Rosetta, and it found really a huge number of these large, complex organic molecules in this particular comet. And ESA very nicely have made this very nice slide, which I think just demonstrates all this chemical complexity in a really friendly way. So this cometary zoo of molecules that have been detected in CG. So you see here a lot of the long carbon chains have been detected, some alcohols all the way up to pentanol. We see sulfur-bearing species. We see organic molecules like acetic acid, acetaldehyde. But the one molecule that I want to point out for the purposes of this talk is the king of the zoo, the lion, and that's glycine. I think Paul already showed you this as well. So glycine was detected by Rosetta on board Rosetta because of its very high precision mass resolution. So it was able to see the fragmentation pattern from this particular molecule. So we know that comets contain at least the most simplest amino acids. And we want to understand how interstellar or circumstellar chemistry helps to make already those very complex, what we would call very complex molecules. So to move on a little bit more into the introduction, the next thing I'm going to cover for the next few minutes is what we already know about the chemical composition and structure of protoplanetary disks. So you can see here a cartoon of a disk around a young star, and the disks are formed out of dust and gas, very much the same material that we have in our molecular clouds. The gas in the molecular, or the volatiles or molecules in the protoplanetary disk can have two phases, very much the same in molecular clouds. We have the gas phase, which is mainly molecular hydrogen, and we have the ice phase, which is mainly water, because oxygen is one of the most abundant elements that we have after hydrogen and helium. So disks are not geometrically thin objects. They actually have some vertical extent that's driven by warming of the gas, by heating radiation by the central star. So disks have this characteristic almost to probably three-dimensional structure. We have a very cold, dense midplane where we can get ices forming very much via the same processes as we see in molecular clouds. As we go towards the surface, this becomes warmer, more irradiated, and this is where we get a rich ion molecule chemistry, which creates molecules in the gas phase. And then towards the surface, this is the most irradiated by the central star, and this is where molecules can be split apart by photodissociation or ionization into atoms and ions. And when we point telescopes at disks, what we're really looking at is this molecular layer in the disk atmosphere. And these observations are very important for telling us something about the temperature and density structure of these objects around nearby young stars. If we look at near-infrared to mid-infrared wavelengths, we're really looking at material very close to the star on what we would consider to be solar system size scales, so within about 10 astronomical units, where an astronomical unit is the mean distance between the sun and the Earth. And in the infrared, we're really looking at vibrational or low vibrational transitions. So we tend to pick up emission from very simple, stable molecules that can survive at those densities and temperatures. Molecules like carbon monoxide, water, acetylene, and other small hydrocarbons like methane. But disks are much larger than this. Sometimes they can be as large as a few hundred AU in radial extent. And this material in the very outer region, which is going to go on to form our comets reservoir, it's very cold. It's only a few tens of Kelvin above absolute zero. And this is where the lower lying rotational transitions of many molecules that we use for diagnostics in space are excited. So we observe those rotation transitions using 7mm or millimeter spectroscopy typically. And here you can see that the molecular inventory then explodes. So not only are we seeing these very simple, stable molecules, we can also see cations, as you heard about. We can see small radicals, such as C2H. And as I will go on to talk about, we're also now starting to see these much larger molecules bordering on what we would consider to be quite complex. And these are what I'm going to focus on today. So the other reason that we're interested in trying to map the molecular structure of disks is we want to gain some insight into what ingredients we have for building a planetary system or a cometary system around the new star. And for this purpose, the temperature gradient in the midplane, so the inner regions of the disk is very warm, close to the star, and becomes colder as you move away. That leads to the formation of what we call snow lines. And different molecules will have different snow lines because they have different volatilities. They have different temperatures at which they will sublimate from the solid phase into the gas phase. One of the most important ones is the water snow line, and especially for the formation of our own solar system. The theory is that the giant planets were only able to form because we had a water snow line that vastly increased the amount of solid material beyond it and allow the gas giants and ice giants to form. Other molecules have snow lines too, so here you can see at 70 Kelvin, we see around that the CO2 snow line, and then further out in the coldest region of the disk, about 20 Kelvin, we have the CO snow line. And this is important because the relative ratios of ices that we have in the disk midplane will then determine the ingredients that we have for building our planets and our comets. And that goes on to have further implications for, as you will hear during this workshop, for molecules you might expect to see in planetary atmospheres. Ices in the midplane can also be subject to irradiation. If cosmic rays can penetrate, they can break apart molecules and trigger chemistry. In the very outer regions, you may even be diffuse enough to be exposed to the ambient interstellar radiation field, which can create some interesting chemical effects in the outer regions. So what is actually dictating the chemical structure of disks? We have a complex interplay between the gas phase chemistry in our disk atmosphere, surface chemistry in our disk midplane, either in our ice reservoir shown here in blue, or perhaps even on bare grain surfaces, which we know is important for the formation of H2. We have lots of different types of processing that can go on. Thermal processing, once our dust grains and ice mantles have warmed up sufficiently close to the star, in the outer regions of the disk, we can get processing through non-thermal processes such as UV photons, X-rays, and perhaps even cosmic rays. So we have this complex interplay between gas phase chemistry, surface chemistry, and all these different radiation sources that we have in the disk as well. And on top of all that, as you heard from Paula, we have dynamics at play. Disks are accretion disks. They're feeding material through themselves onto the star. And if there's some turbulence injected in there from the formation, then we can get actually perhaps quite a high degree of mixing going on between the icy regions and the ice poor regions in the disk. So just to move on to what we're actually doing from an observational perspective to understand more about these larger molecules in particular, I'm going to now talk about ALMA, the Atacama Large Millimeter Submillimeter Array that you've all heard about before from the other speakers. So ALMA is a very important tool for us because we need very high spatial resolution and very high sensitivity in order to try to see these larger molecules in these objects. This is just a little cartoon to demonstrate why that's difficult. So disks are on the order of a few hundred astronomical units in size, and the nearest ones are of the order of about 100 parsecs away. And that means in astronomical terms, they're actually really tiny objects. They only span a few arc seconds on the sky. So if we want to map what the dust continuum and molecular line emission looks like, we need resolution, sub-arc second resolution, which is what ALMA gives us. Further to that, the outer cold regions of disks also emit predominantly at long wavelengths. So we need a telescope that can see at sub-arc second resolution with high sensitivity that emission from the outer regions of the disk. This is what ALMA gives us. It does dust and molecules from 84 to 950 gigahertz of very, very high spectral resolution, well above 1 part in a million, a huge collecting area with 66 antennae, giving us sensitivity, and the baselines, up to 16 kilometer baselines, allows us to, of the order of a resolution to observe the dust of about 1 astronomical unit in the nearest object, and the molecules we can get down to of the order of 10 astronomical units. So ALMA is really allowing us to map what our dust, our planet-building material, and our gas, our molecules that will go into our comets and forming atmospheres on spatial scales very similar to the size of the solar system, and really for the first time. So just moving on, I'm going to now talk about what ALMA has revealed about the abundance and distribution of complex organic molecules in protoplanetary disks. So Paula already showed you this discovery before. I'll just go over it again. So the first molecule with 6 atoms or more that was detected in a protoplanetary disk was methyl cyanide, CH3CN, and that was detected in a disk called MWC 480, which is a disk around a relatively higher mass star than the Sun. So an effective temperature of about 8,000 Kelvin. So this disk is a bit warmer than perhaps the disk around the young Sun would have been. This is the 2 lines that were detected, so the J equals 14 to 13 transition, and 2 of the K ladder transitions within that J transition. And this is a relatively warm transition. It's an upper energy level of about 100 Kelvin. So we think that we're tracing quite warm methyl cyanide in this object. And once we have that detection and do some modeling, we can also compare the numbers that we get with what we observe in comets. Methyl cyanide has been observed in quite a few comets. So here I show the status in about 2011. In red, you can see the number of comets in which methyl cyanide has been observed from the Oort cloud, OC, compared also with that observed from the Jupiter family comets, the JF. And the abundance relative to water is on the order of 0.01%. So given that we have this data from the comet, we can take the observations with ALMA that we make towards the young disk, and we can compare the 2 ratios. Now, unfortunately, we do not have water in MWC 480 because water is quite difficult to observe. We need to go to space, and we need another Herschel to do that. Hopefully, we'll have one in the future. So instead, we can make a comparison not with water, but with HCN, which is another molecule well observed in comets and protoplanetary disks. And what Oberg and collaborators found at that time was that the ratio between methyl cyanide and hydrogen cyanide was between 5 and 20%. And that's of the order of what we see in comets, which is about 10%. So this is the first clue that what we're seeing in the gas phase is potentially representative of what's happening in the icy midplane. So methyl cyanide, we now know, is quite an abundant molecule in protoplanetary disks. We now have detections in 4 and another detection in a tentative detection in 5th protoplanetary disk. So this makes it quite a powerful tracer of disk physics and chemistry. So the next molecule that we went to look for was methanol. To do this, we pointed ALMA at our nearest protoplanetary disk, TW Hya, which is only 54 parsecs away, so it's relatively close to us. And it's a very well-studied object, so we think we know a lot about it. It's a little bit bizarre, but it's still quite well-studied. And it's a cooler star, so it's an effective temperature of about 4,000 Kelvin. So a little bit more akin to what the disk that we might have expected to be around the young Sun. Methanol was an important molecule for us to go to target because we know it's abundant in interstellar ices. And the other thing that we know is if you shine UV light on methanol ice, you make a lot of other complex molecules, things like dimethyl ether, glycolaldehyde, and so on. So we know that methanol is an important feedstock for building complexity in ices in space. So we pointed ALMA at TW Hya, and after a lot of data analysis to make sure that we had a clear detection, I show you here the spectral line that we see in orange with the model fit that we did to the data in green. So we had a nice greater than 5 sigma detection of methanol for the first time in a protoplanetary disk. Just to show you what methanol, the status of methanol in comets looks like, I show you the same plot as before, except for methanol. This is the number of comets. And on the x-axis, we have the abundance relative to water for, again, our red Oort cloud comets and our blue Jupiter family comets. And you can see that there's a bigger spread in abundance between a fraction of a percent up all the way up to 7 or 8% relative to water, with a peak around about 2 to 3%. So we have around 8 or 9 comets now with that abundance distribution. So one of the good things about TW Hya with its proximity is we were able to detect water in TW Hydra. That was work by Ted Bergen and collaborators, Mikhail Hoger-Heidi and Niels Cleves, who you'll hear from as well. And so then we can make a comparison with the methanol we see in TW Hydra, with that detected with Herschel for water. And the ratio that we get out of the observations is between 1 and 5%. So actually, again, very consistent with what we see in cometary coma. So I'm going to include this detection here as well. This is the detection of formic acid in TW Hydra. This was done by Cécile Favre and collaborators only very relatively recently. The paper came out about 2 months ago. And although formic acid isn't a complex organic molecule in our true sense of the definition in astrochemistry, it's only got 5 atoms, it is quite a complex, it's an organic acid. So I include it here because, again, we can compare that with what we see in interstellar clouds and also in comets. This is what the detection here looks like. This is the asymmetric rotor. They have the 616 to 515 transition here, quite clearly detected at the expected source velocity. And then this is in the bottom is the integrated intensity. This is done in band 3 of ALMA. So the beam here is quite large, of the order of 200 or more, maybe 300 astronomical units in diameter. But what the Favre and I were able to show is that the formic acid is actually quite extended. And this is quite different to what we see for the methanol, as I will show you towards the end of the talk. So what Favre and I did was look at the abundance of formic acid that they see in the gas phase, with that relative to methanol, which we also saw with ALMA, and the ratio there is of the order of 1. And if we compare that with what we see in comets, it's at the upper end of the cometary range, with, again, a little bit of a spread over 2 orders of magnitude. So at least some similarity with the cometary composition we are now seeing in these larger molecules. So for the final few minutes of the talk, I want to talk maybe a little bit more, now that we have these detections, some of the theories over why we're seeing them in the abundances that we are, why that might be tracing the ice reservoir, and we can make that comparison with comets, but also some of the open questions that we have on the abundance and distribution that we see in the models. So as I said at the start of the talk, we make these observations in the gas phase, and we're really probing the gas in the atmosphere of the disk. We're not necessarily getting deep down into the midplane. So some of the theories that we have for the origin of these complex molecules, so as Eric told you, and I think Paula as well, there may be possible gas phase routes that we haven't considered so far that's allowing these to form in the gas phase. The most favored route that we use in the models that I will show you is that we have surface chemistry formation within the ice mantles and dust grains, and then we have non-thermal desorption via photons or X-rays that can knock the molecule back into the gas phase where we detect it. And another open question on this is how important is ice processing, because UV photons and X-rays can also destroy molecules and also, in a way, trigger complexity as well. If we shine UV light on methanol ice, for example, as I've said, we actually see quite a lot of other larger molecules formed, even at low temperatures, 10 Kelvin. So we can, to try and give some insight into this, we can model the chemistry using a large chemical model with lots of bells and whistles. We put everything in. We use a template structure for the disk, and then we can look at what the distribution of the molecule looks like. And I show this work here. So in blue, you see the column density that we fit a model to the data. That was what we used to fit the data that I showed you previously for methanol. And it suggests that we have a ring structure of column density with a peak around 30 AU. When we compare that to a full bells and whistles chemical model where we have gas-based chemistry, ice chemistry, etc., you can see that it's this purple curve here, and we see a lower column density overall and a much more extended distribution. And just to remind you that the purple line here is our model fit to the data. So it appears that the models that we have predict extended methanol emission, which is in disagreement with observations. And the chemical origin that we need in the models to reproduce the methanol, at least in the outer disk, is photodesorption, the interaction of UV photons with the ice. The other interesting thing about this distribution is that it appears to peak around about where we know the CO snow line to be in TW Hydra. And that points towards maybe some coupled chemistry between CO as it desorbs and accretes onto the ice mantle in and around its snow line, and that of methanol, which we know forms from the hydrogenation of CO. And that's a bit of an open question that we're trying to understand better at the moment. So one of the other issues with methanol is that recent experiments trying to measure the photodesorption yield in the gas phase when you shine UV light on methanol shows that it fragments when it photodesorbs. So instead of the molecule coming off intact, this is very much akin to the dissociative recombination issue that Eric also mentioned. The molecule actually fragments and smaller fragments come off into the gas phase like CO, methane, and oxygen, things like that, the hydroxyl radical. So when you put those numbers from the lab into a model, and here I show now a slice in the disk from the midplane, which is at 0 here, up the disk atmosphere on the x-axis, and then the number density is on the y-axis. On the left-hand side, you can see methanol ice in blue. On the right-hand side, you can see methanol gas in the red and orange. And shown are the fractional abundances at different time steps between half a megayear all the way up to 10 megayear. Now, in our canonical models, where we use the measured photodesorption yield from many years ago, we actually match the abundance of methanol that we need in the gas phase in the disk atmosphere. As soon as we switch on this fragmentation, the abundance drops down to these solid lines by of the order of 3 orders of magnitude. So it's a very destructive process. Not only does it limit the amount of methanol we have in the gas phase, over time, it also eats away the ice reservoir as well. So with fragmentation upon photodesorption, we reduce the peak abundance of gas phase methanol, and our methanol ice gets eaten away with time as well, as it's converted into other things. This is some work, this is in the paper by Ryan Loomis. This is the detection of CH3CN in TW Hya. The modelling was done by Ailsa Cleves, who you'll hear from this afternoon. And one of the interesting things about this modelling work was that if we include only gas phase chemistry for methyl cyanide, we do not match the column density that we need to reproduce the observations in TW Hya. It's only when we have ice chemistry from forming methyl cyanide do we reach the abundances that we need to explain the observations. So one of the nice results from this is that it does predict the right distribution of methyl cyanide. The ice chemistry is needed, and the origin, again, is photodesorption. One of the problems is that we can't quite match the cometary abundance in the midplane. We can match it well in the disk atmosphere, so this points towards perhaps maybe some degree of vertical mixing, helping to increase chemical complexity in the disk atmosphere and the ice that is then perhaps transported back down into the disk midplane. The alternative explanation to this is that the ice in the disk actually is inherited. Some of the methyl cyanide is formed earlier and is inherited by the protoplanetary disk. So I'll just show you quickly some of the results for formic acid, again in TW Hya. Here you can see now two-dimensional abundance distribution again. So this is the radius in the x-axis, and we have the height in the y-axis, and the color map is the abundance relative to molecular hydrogen. On the left, we have the gas. On the right, we have the ice. So you can see the ice is confined to the midplane for the most part, and we have the formic acid popping up in the disk molecular layer, which is where we would expect it. In this model, they actually do a fairly good job at reproducing the distribution and column density. So the observed line here is in grey on the far right-hand side, and then the blue shows you the model column density, which is close to within a factor of 10 or so of the observation here. So the formic acid agrees well. The chemical route, again, is chemical desorption and photodesorption from ice mantles. Chemical desorption is another non-thermal mechanism by which you use a leftover energy from bond formation to release the molecule from its busy sorbed potential well in the ice mantle. So I hope I've shown you in the past 25 minutes or so, with the high sensitivity and high spatial resolution of ALMA, we can for the first time go and look for these larger molecules in protoplanetary disks and better make the connection with what we see there with what we know from the comet inventory. And that helps us better ascertain how important chemistry, either before the disk formed or during disk evolution, is in setting the chemical complexity that we see in comets. We have methyl cyanide in TW Hya. Also very recently in D4046 Sagittarius, methyl cyanide is now very well detected in 4, if not 5 disks. We have formic acid now recently detected in TW Hya. So we know these molecules are there, and we've been able to do these very challenging observations thanks to the high sensitivity and spatial resolution of ALMA. Just to finish, I just want to say something about some next steps. So, of course, we can also always go to higher spatial resolution. This is the resolved emission of methanol from cycle 2. With cycle 4, we have much better spatial resolution, and we can now better see the radial distribution of methanol. And we think that it's tracing the location of the millimeter-sized dust grains, which is shown here by the grey contour. The other thing that we can do is we can try and get individual line transitions, which gives us excitation information. This is, again, the cycle 4 data of methanol in TW Hya, where we resolve 4 transitions. This will give us excitation information and will tell us where vertically the methanol emission is coming from. What I can tell you is that we only see lines with low upper energy levels. We do not see this line here at 293 gigahertz, which is an upper energy level of 63.7 Kelvin. So we're really seeing cold gas. And so we're suspicious that this is actually coming from quite deep down in the disk. We're continuing efforts with ALMA. We actually have an ongoing ALMA large program, tentatively titled The Chemistry of Planet Formation, where we're looking at 5 disks with very high spatial resolution of the order of 10 AU in all of the molecular tracers that we know of so far across different wavelength bands. That amounts to 130 hours. This is really a global effort, as Mike pointed to. So we span 4 continents here, North and South America, Europe, and East Asia as well. And I actually got an email to say that the first data set was available for download just before this workshop started. So that's actually quite scary and also quite exciting at the same time. So that's starting. Keep tuned for that. Additional molecules to target, we can make synthesized spectra to see what would be good to go for. I show here a formic acid, which has now already been detected. I think that we could probably do some of the nitrogen-bearing species. I think that formamide might actually be a good target to go for next, and it also has more closer prebiotic chemical connections. And then just to finish with some open questions, I think that we have some ideas, but the gas phase origin of these large organic molecules in disks is still a bit uncertain given some of the disagreements between models and observations. We have to ask ourselves if what we're measuring in the gas phase is really reflective of what we see in the ice composition, or if other processes, intermediate processes, change that abundance. We also have to answer the question if all large molecules actually fragment upon photodissociation. This is a mechanism that we rely on in many cold environments to explain the presence of these large molecules we think are formed in the solid phase, in the gas phase. We need to understand something more about how X-rays, young stars are very bright in X-rays, or indeed even cosmic rays, whether they lead to destruction, fragmentation, or if they actually enhance chemical complexity. We need to get a better handle on the treatment of so-called chemical desorption, as some models really rely on it as the mechanism to keep these molecules in the gas phase at low temperatures. And as you've heard, there's a lot of debate now opening up on whether we are missing quite important gas phase routes towards some of these larger species as well. So I'll finish there with those open questions, and thank you for listening.
Are there questions? Yes.
Oh, okay. Hi, can you hear me?
Yes, I can.
Okay, great. Jake Yeston from Science Magazine. I'm curious if you could explain to those of us who are a little bit unfamiliar with comet dynamics, what's the process for the comets picking up these molecules versus the molecules forming in these disks? And are those processes assumed to be the same, or is it sort of 2 different processes happening that lead to the same outcome?
So I didn't quite hear the first bit of the question. So are you asking about?
In other words, you were comparing what's in the disk to what's in the comet, And
Yes,
so
so
I mean I'm a little bit embarrassed. I just don't know a lot about comet dynamics. So I was just trying to understand, is that because the comets pick up these molecules directly from the disk, or is there sort of a different process that happens to form them on the comet that you sort of make an analogy to what happens in the disk?
So yes, I understand you better now. So we think that comets will form from material in the disk. So in young disks, what you have is a distribution of gas and dust. Usually the dust grains are relatively small, maybe up to around a millimeter or slightly bigger in size. And these millimeter-sized grains will have ice mantles on them in the cold outer regions of the disk. And then how comets form, we think, is from the coalescence, the sticking of these ice-coated tiny dust grains, okay? So you go from something that's millimeter-sized all the way up to something that's kilometer-sized. Now, there's a lot of physics that I've kind of glossed over there because you have barriers en route to growth, but ultimately the small grains that we look at in disks that are ice-coated are the feeding material for comets now in the solar system. So that's why we think that comets are relatively pristine. They have stored in their ices the composition of the ice on these small grains that we're now looking at in the protoplanetary disk.
Okay.
So to some extent, we feel that we're looking kind of at the same material, but at two very different points in time.
Okay, thanks.
I have a question or a comment. Oh, yes. Right. Sorry. Anyway. So maybe about 20 years ago, there was another stage in which people worried about intact desorption of molecules versus, right. So a famous chemist by the name of Dick Zare studied it, and they found, even using lasers, that they got intact desorption of some rather big molecules.
Mm-hmm.
Anyway, it's a comment, but we seem to have... Go ahead.
Yes, I think it's all to do with how the molecule redistributes the energy that it has, right? Eric, you're the chemist, so you maybe know better than I. So when I talk to people about this process, if the UV photon is absorbed by the molecule and it has degrees of freedom in which to dissipate the energy, including fragmentation, then that's the path that it may take. I don't know about your feelings on chemical desorption. When I talk to people like ALMA, she's a little suspicious that perhaps the same thing might be able to happen. That the larger molecules are just floppy and have enough degrees of freedom and can kind of dissipate their energy instead of breaking the bond, the physi-sorbed bond between the molecule and the surface. But I think it's something that we can probably approach from many different angles to try to understand better. In that case, I write this. So the lab community can help us, I think, with these questions.
So, Eric,
yes.
It looks like since we're already about 20 minutes over schedule,
okay.
I think why don't we call it there and reconvene from our break. We're going to take a break from right now until about 10:15, and we'll start again right at 10:15.
11:15.
Sorry, 11:15. Wow. Central Time. Thank you.
Okay. And let's thank the speaker once again.